In this demonstration, I would like to introduce the method of variation of parameters. And I would like to discuss this in the context of second order differential equations. And it can be extended with the same uh, analogy to the higher order differential equations. So the method of variation of parameters is required for linear differential equations. If I write the structure for the second order, so it is a of x y double prime plus b of x y prime plus c of x y, and it is equal to f of x. This is the linear second order non-homogeneous differential equation. So for this differential equation, we can write the solution with its two solution. One is going to be the homogeneous part, where we consider this f of x to 0, and the particular solution, which is when the transient condition f of x is applied and for the time it prevails. So we found the simple case when A, B, and C were constants. So we learned that we can use the auxiliary equation. We develop the roots of auxiliary equation, and we can develop the solutions, homogeneous part, of course. And then if f of x is a simple function like the polynomial or the exponential function or a sinusoidal function or their combinations, their products, then we can use the method of undetermined coefficients. However, if this is not the situation, then we have to go for the method of variation of parameters, and this is due to the eminent mathematician Joseph Louis Lagrange. So the method begins that uh, we must have a knowledge of the homogeneous part. So homogeneous part is known. So y homogeneous is known. So we can write C1 y1 of x and C2 y2 of x. So now to write the particular part, we assume that the particular part is going to be a solution which is independent of y1 and y2, the parts of homogeneous solution. So therefore, it will be it will be uh, some function of u of x times y1 of x plus u2 of x times y2 of x. So this is going to be a candidate solution which will satisfy the non-homogeneous equation. So let's see whether it leads to a generalization. Well, of course, it led to a generalization to Lagrange. So therefore, it will lead us to that generalization too. So let's develop that one. So any candidate solution will be accepted if it is going to satisfy the original differential equation. So I require the first derivative, so yp prime. So for simplicity, I'm reducing the notation. So I will write u1 y1 prime plus u1 prime y1 plus u2 prime y2 plus u2 y2 prime. This is going to be the first derivative, and the second derivative with the product rule to all the terms. So it will be u1 y double prime plus u1 prime y1 prime. So this is due to this term, and then this will be u1 prime y1 prime plus u1 double prime y1. So this is due to the second term, and similarly, uh, it is going to be, yeah, u2 y2 double prime plus term similar to that one will be 2u1 2u2 y2 with single prime plus u2 double prime y2. The next step is to look for the conformance of condition that it will satisfy the non-homogeneous equation. Uh, so I can write a of x. So this is a variable coefficient, however, still a linear differential equation. So yp, the second derivative. So u1 y double prime plus 2u1 y1 single prime plus u1 double prime y1 plus u2 y2 y double prime plus 2u2 prime y2 prime plus u2 y double prime plus u2 double prime y2. So this is ax y double prime plus bx times y prime. So I'm just trying to satisfy this equation with the particular part. Okay. So let's move on. We have to be patient. However, it is a simple algebraic calculation. So the first derivative, u1 y1 prime plus u1 prime y1 plus u2 prime y2 plus u2 y2 prime plus cx and okay, u1 y1 plus u2 y2, and it is then equal to f of x. So here we can collect the terms by noticing that y1, we will notice that y1 and y2, these are the solutions of the homogeneous differential equation. So if I collect the term, the u1 y double prime, well, it is with the 1, u1 y1 double prime, so a component of A, and then a component of B, which is with the first derivative of y1, and the first term with the C. So in these terms, I can pick up u1 as common. So I will find a structure ax u1 ax y1 double prime plus bx y1 prime plus cx y1. And similarly, there is going to be another structure with u2. So where it is here. So let me pick that up from here. So this one u2 y2 double prime, and similarly from bx u2 y2 prime, this one, and then u2 y2. So I will have a similar structure here, which is A, AX by 2, the double prime, plus BX by 2 prime, plus CX by 2. So these terms have been collected, and then let's write the remaining terms. So I have AX. So from the first part, it is 2 times U1 prime by 1 prime plus U1 double prime by 1 to U2 prime by 2 prime plus U2 double prime by 2 plus BX. Okay. U1 prime by 1 plus U2 prime by 2, and the coefficients of Cx have been collected in the first two terms, so then it is finally equal to f of x. Okay, so now we can notice the solutions y1 and y2. These are the solutions of homogeneous differential equation. Therefore, they will be set to 0. So this part will vanish, and also this part is also going to vanish. Okay, so the 2 will vanish, and we are then left with these terms, right? So let's write it one more time. So for simplicity, I write here A. So it is understood that it is variable, a function of x. So we can notice that the term with B has its derivative over here. So for example, if I look for its derivative, so it will be u1 prime y1 prime plus u1 double prime y1. So this term is available. This is this term, and u1 y1 prime, it is available over here. So I can write ax. So u1 prime y1 prime, and similarly one term from here, u2 prime y2 prime plus okay, let me write it for the time being like this. Okay, then it is okay. Let's write it one more time. u1 prime y1 prime plus u2 prime y2 prime and plus, well, this was just for the demonstration. This was derivative, just to notice that. Okay, then the term u1 double prime by 1 plus u2 double prime by 2, these are with A, and plus B of x component u1 prime by 1 prime, u1 prime just by 1, u2 prime by 2, and it is equal to f of x. Okay, so I can notice that u1 prime by 1, its derivative is within these two terms. So if this term is collected with this term, then they constitute the derivative of u1 prime y1, and similarly Okay, this term u2 prime, y2 prime, and this term u2 double prime, y2. This is the derivative of this one. So we can write these four terms as the derivative of the component which is with b of x. The rest can be written as such. So here ax u1 prime y1 prime plus u2 prime y2 prime plus a of x, and then I can write derivative of the component with b of x. So u1 prime y1 plus u2 prime y2 and plus b of x times u1 prime y1 plus u2 prime y2, and it is equal to f of x. And now this is a very interesting situation. Here we have one equation. This is one equation, and we have two unknowns. Our unknowns are u1 prime and u2 prime. These are the unknowns. However, we have one equation. So this is a situation where we have to impose some special condition. So I generally share this kind of analogy that if I have a resultant vector and I would like to look for its components, so I develop the first component. Then the second component will be the one that will satisfy a condition that it should meet the first vector at the tip of first, and it should conform to the tip of the second vector at its own tip. So they are going to exist in the form of pair. So if you have known one condition, the second will satisfy the other condition that can be evaluated. So another simple analogy is that it is if it is known that for two numbers x and y, we have the sum equal to 10, then there is no way to come up with the unique values of x and y. So we have to fix one value and we can generate the other. For example, the x and y pairs can be 1 and 9, 2, 8, and it can be extended to infinite number of pairs. With this analogy, now we are going to introduce the condition, and the well-known condition uh, is that we consider this component to be equal to 0. So we assume one condition. So u1 prime y1 prime y1 plus u2 prime y2, it is equal to 0. So this condition generates the other condition by itself, that if this is 0, this will also be equal to 0. And then we have the remaining condition as ax times u1 prime y1 prime plus u2 prime y2 prime, and it is equal to f of x. So we have generated the second condition. So first condition and the second condition, which is simplified to u1 prime y1 prime plus u2 prime y2 prime, and it is equal to f of x over a of x. So in some notations, people start with the equation where people start with the first equation by dividing a of x throughout. So that's the other notation. So the two equations can be solved. These two equations can be easily solved by using the Cramer's rule. So let's write it in the matrix form. So it becomes y1, y2, y1 prime, y2 prime, and then the unknowns u1 prime, u2 prime, and over here it is 0 and f of x over a of x. So this can be solved. So it is a linear equation of the type ax equal to b. So this is the matrix form, and x, the unknown vector, it is equal to A inverse times B. So this is its form. And we can solve this one by Cramer's rule. It requires the condition that the determinant of A should not be equal to 0, which is the singular matrix. And in our case, this is a very interesting determinant y1, y2, and y1 prime, y2 prime. So this determinant, when evaluated, it is y1, y2 prime minus y1 prime, y1 prime, okay, y1 prime, y2. So this determinant is a special one, and we introduced that one earlier. It says that the two components of the homogeneous solution, they are linearly independent. So this determinant is known as the Wronskian determinant. We will represent it with the W, and it is the condition of independence of the solutions in the homogeneous part. This is known as uh, Wronskian determinant. So then we can calculate the u1 prime and u2 from those equations using the Cramer's rule. Okay. So let's write the equations. Okay. So u1 prime, so 0, f of x over a of x, and then there is y2 and y2 prime. That's the way we apply the Cramer's rule, and divided by the Wronskian determinant. So it is u1 prime. So it will simplify to minus y2 of x times f of x over a of x, and whole divided by the Wronskian. And it means the u of x, u1 of x, will be evaluated from the integral. So minus y2 of x, f of x over a of x, or w, and dx. So this integration would yield the evaluation of u1 of x. Similarly, u2 of x will come from the determinant, Cramer's rule. So the first column will survive from matrix A. So y1, y1 prime, and the right hand side over a of x, and whole divided by the Wronskian, and its integration would lead to the evaluation of u2 of x. So it will be y1 of x times f of x over a of x over w dx. So after getting u1 and u2, we will be able to write the complete particular solution. So particular solution which satisfies the equation, and we found it is u1 of x y1 of x plus u2 of x times y2 of x. So finally, we will be able to write yp of, the complete solution y of x with the homogeneous part and the particular integral. So c1 y1 of x plus c2 y2 of x plus u1 x y1 x plus u2 x y2 x. So this is the strategy, which is method of variation of parameters. So this strategy can be directly implemented for the cases in which the we have a general uh, linear linear non-homogeneous equation. So this can be extended to third order differential equation. In the third order differential equation, of course linear, if I write the structure. So the structure of a third order equation is, for example, a3 of x y triple prime plus a2 of x y double prime plus a1 of x y prime plus a naught y, and it is equal to then f of x. So we have to uh, generate the Wronskian, uh, and for a third order differential equation, of course, we must have three components in the homogeneous part. So the Wronskian will be a 3 by 3 determinant like this: y1 prime, y2 prime, y3 prime, and then y double prime of 1, y double prime of 2, and y double prime of 3. And of course, this will come from the three equations. So let's discuss the examples related to the Wronskian um, determinant and the method of variation of parameters in the next video, as we are getting uh, as we are running short of the time provided for one video. So stay connected.